this NAQ is now finished. That's not relevant. And then we do these training sessions every Wednesday, and every Sunday we do the mock competition. And you start at 1, Ricky?
I'm trying to get a room from GDSC.
Yeah.
So whenever I get that, I'll announce it.
But oh, you're talking about the other, you're talking about your,
Yeah.
oh, I was talking about the mock competition. So the mock competition is still at 1 o'clock, right?
Okay,
Sundays?
Yeah, 1 o'clock Sundays.
Okay, and you're planning on what day for your sessions?
Either Thursday or Tuesday. One of
Okay, okay, fine. Pretty soon this room may not be available for us. They're doing some renovations, and so we may have to find another room, but I'll try and take care of that and announce that. What else? Yeah, so we're going to talk about counting permutations and combinations. Most of these you have seen. I'm going to wear this mask because I have a cold and I don't want you guys to be sick. I really need you to compete. So we're going to talk about some counting problems. Should I set up Zoom? Probably, right?
Yeah, that's fine. I can announce it.
Okay. All right, so let's talk quickly about counting and permutations and combinations. This is part of things that I did last year, so some of you may have seen it. Where is my mouse? Here. Okay. So we're going to start with some simple questions, and some of you may have seen this. If we want to form a team of K students from a class of N, how many different ways are there? So it's N choose K, right? You've seen this before. You don't need to know the formula for it, but the easiest way to remember this is N choose K. Somewhere in your book, somewhere there's a formula, and the formula is N factorial divided by K factorial times N minus K factorial. If you don't remember it, it's okay, because most of these competitions we take cheat sheets where we write down all these things, okay? So N choose K, it simply says from N, how do I choose K? And that's the number of ways to do it, okay? Any questions about this? All right, so that's very basic. Here we are assuming that all the students in the class are distinguishable. Namely, Ricky is very different from Yash, who's very different from Neeraj. But what if they're all identical? How many different ways can you pick K students out of N? If you're all clones of each other, there's only one way to do it, right? Every team looks the same. So there's only one unique team that you can form. All right. What if you have a bunch of female students and male students, maybe even some non-binary students? If you have categories, then how do you pick a team that has exactly this many girls and exactly this many boys, or the two categories, given the total number of girls and total number of boys? So here you have to take it apart, right? But for each number of girls, there may be a different number of boys that you have to make up on the team in order to make a but here you're told it's exact, so it's relatively easy. It's going to be from the B number of boys you pick B, and from G number of girls you pick this many girls. So it's just a product, because for each choice of the boys in the team, you have an independent choice for the girls on the team, right? So that's why it's going to be a multiplication, not an addition. Is that clear? Okay. Now, if I were to tell you, well, actually the answer would be different if I said at most G girls and at most B boys. Then it becomes a little bit harder, because then you may have different choices of the value of G, and you may have different choices for the value of B, and each one gives you a different combination. I'll let you figure that out. But next, what if we have to line them up? So if you have n students, and if you want to line all of them up, how many different ways can you do this? This is n factorial. This comes from permutations, because you're trying to permute. But what if you only want k of the n students? Sorry?
That would be npk instead of choosing k.
You could use npk, but you could also use n choose k and then do a factorial on those, right? Yeah, it'll be exactly the same. So it could be n choose k multiplied by k factorial, which is the number of ways you can line them up, or equivalently you could call it npk, which is a slightly different formula. Anyone remember the formula?
Factorial by n minus k factorial.
Right. So it's just n factorial divided by n minus k factorial, right? Or is it k factorial, or does it matter?
N minus k factorial.
Well, you want to keep the k factorial, so it must be divided by n minus k factorial. Okay, good.
Sorry, Professor.
Yeah.
For the previous one, for number two,
Uh-huh.
how many ways do we form G girls and B boys?
Right.
Can you explain again why we multiply them?
Well, because the choice of boys is independent of the choice of girls.
Oh,
If
I see.
If I want two boys and a girl, I could pick you two and her, or I could have picked these two guys and her. And it's an
Oh, I
independent
see.
choice, right?
I guess it's basically like it's like in probability when you have independent events.
Right. So you have to
I
know
see.
when to add the counts and when to multiply the counts.
Oh.
So that's the only thing you have to be careful about, and it's very similar to probability considerations. You're
right,
right.
because when they're dependent events, that's when you add them, right?
Well, if they are, when do you add them? Well, you add them if, so for instance, if you, if there are different ways to do it, let me see, when do you add them? Is there a simple way I can explain?
Like the case of up to B, then you add ways to choose 1, choose the 2, choose the 3.
Right. Okay, that's a good example. So let's say that I told you that I want a team of 3, but I want at most 2 boys and at most 2 girls.
Okay, okay.
So now I could form a team with 1 boy and 2 girls,
Right, one
or
boy,
2
yeah.
boys and 1 girl.
Right, I see.
Okay.
Oh, okay.
And
right, yeah.
I need to count the number of ways to do one boy and two girls, and I need to count the number of ways of doing two boys and a girl, and those I will have to add, not multiply.
Oh, I see. I guess in this case, right, because it's up to.
Well,
like you said,
it's got
like an
it's
up
got
to case
doesn't have to
where
do
you
with up to. It's got more to do with counting. You're essentially counting, and
Oh, because you're counting the number of ways that you could do two boys and one girl, and the number of ways like you can
Right.
do two girls and one boy.
correct.
Oh, I see.
Yeah, and they are independent. So.
Oh, okay.
So it's still independent. It's got nothing to do with dependence, but they are. But
Number of people we have to choose for first case. Like 1 and 2 and 2.
no, his question is why are you multiplying sometimes and why are you adding sometimes? And I'm trying to explain this and I am struggling. Don't have a good way of explaining that. So if you're looking at cases, right? If it's either case 1 or case 2 or case 3 or case 4, then you have to add them up, assuming that they are independent. On the other hand, if the choices all go towards case 1, so let's say I want 2 boys and a girl, right? How many ways can I do this? Well, there are whatever 10 boys here. Of these, I want two of them. So 10 choose 2. And then I also want girls, and there are 2 girls, and I want 1 girl. So 2 choose 1. So there I have to multiply because the choice of boys has nothing to do with the choice of girls.
Okay. Okay.
It's independent, but for every choice of 2 boys, I can try each of the choices of girls. Does that make
Right.
sense?
For each of the choices you have of
Right.
of picking
Yeah.
of picking boys.
So for
you can,
every
like,
choice
choose
of
girls.
boys,
Yes.
I can try all possible choices of girls. But if I want to look at 2 boys and a girl and 2 girls and a boy, those 2, I'm not going to do them simultaneously, right? So for every choice of 2 girls and 1 boy, there's nothing to do with the choice of 1 girl and 2 boys, right?
Sorry, the second case that the second case is not as clear to me.
Well, these are cases. So either this is going to be true or this is going to be true. And I'll count the number of ways of this, and I count the number of ways of this, and I add them up. That's all.
Oh, I guess it's either this. I guess it's a
Right.
case when it's either this or this.
Right.
Oh, I guess that's when you add.
Yeah.
Like
yeah.
I don't know. I know it's not about.
I don't know. Is there a
independence,
better
but
way of
they're
explaining
like,
this?
I don't
Anybody
know,
else?
So for the second one, it's kind of like thinking for every one choice that you make, for example, for the boys, you need to make a multiple number of choices for the girls.
There are multiple choices for the
Exactly.
girls.
That's why you have to multiply. Because it's very
By the way,
so,
Dr. Giri, the slides aren't updating on Zoom. People just see.
let's say you have 1 boy,
First
right?
slide.
Okay.
And 10 girls, and you're trying to pick 1 girl from the girls. How many times are you going to have to choose? Like how many different choices can you make?
Okay, so yes, you have 10
different choices.
Ah,
So 1
yes.
times 10.
Oh, I
Now?
see it. Or but if you have 2
Okay, now
boys,
it's
but if you have
Yeah.
2 boys and 10 girls, you would have 2
2 choices for the boys and 10 for the girls.
So then, yeah,
Two
that makes
times
sense why you multiply them.
You get it?
Okay, yeah.
That's it.
I mean, I
Yeah.
guess the case when you add it, that's different.
Yes.
Okay. All right. So I have one more problem here. This time they're not standing on a line, but they're sitting on a round table. Sitting at a round table. You have n people. How many different ways can you arrange n people at a round table?
Is it not n minus 1 factorial?
Yes, it is. But why?
I don't remember.
Anybody? Why is it n minus 1 factorial?
You have n factorial ways to choose it, and if you rotate it, you can rotate it n times.
Yeah, if you just take n factorial, then you're going to overcount because if you just rotate them, that's going to give you the same order at the table, right? Relative order. So you don't want to count the same thing over and over again. How do you take care of this? Well, you fix one person. You say, Ricky, you're going to sit here, all right, at this chair, And then you take the n minus 1 people and arrange them any way you like. And that's n minus 1 factorial. So now it's like almost like placing them on a line. So that's why it's n minus 1 factorial, right? So these are all simple ones that you should just intuitively know. It's a good idea to get familiar with them so that you can quickly get to the answers. Otherwise, you're going to struggle with the basics. And then it'll be harder to deal with more complicated cases. Okay, so let's continue. I need to close this. You're given n students. How many ways can we form a team with at most m members? Well, slightly different here because it says it's at most m, right? If it's exactly m, we know it's n choose m. If you want at most m, then you have to add a bunch of things. This time again, you have to add. And why is it add? Because if you choose m people, that's one case. If you choose m minus 1 people, that's a different case. It's m minus 2, it's a different case. And then each of these will give you independent answers, and so you add them up.
Oh, because you have n students. I guess you're not necessarily choosing n students, I guess.
So again, so the answer here is a summation. That's n choose k, but k goes from 0 all the way up to n, right? Okay. Again, you can ask the question, what if they are indistinguishable? Then each one, it's just the number that you care about because they all look identical, right? So it's got to be m. Well, actually, it's m plus 1, right? Because you also should take 0. It should be m plus 1. That's slightly off. All right. What about this harder question? You've got n workers, and you want to break them into teams. The first team has this many people, second team has this many people, and so on. So you want to take the entire class and break it into smaller teams. So the first team I want is 4, second team I want only 1 person, third team I want 3 people, and so on. How many different ways can I form teams from the entire class? Okay, this one looks a little bit harder, but you can kind of work this out.
N choose, let's say, like 4, 5, 6. N
Yeah.
choose 4, then n minus 4 choose.
That's right.
5.
So you take the remainder, and then you choose 5 out of them. Then you take the remainder again, and you choose 6 out of them, and those will be the remainder anyway, so it'll be 1. There's a simpler formula for writing it. It's called n choose n1, n2, nm. And it's a simple formula. Again, it simply says n factorial divided by n1 factorial, n2 factorial, nm factorial. So you just multiply the factorials in the denominator.
Oh, what did you say it's called? The formula?
It's called a multifactorial formula. Okay, any questions about this? So essentially here, what would the way to think about this is actually quite simple. So if you have n people, there are n factorial ways to order them, right? But from the n factorial ways, so let's say I line them up on a straight line, and then I break them into the teams that I want. Okay. So I line them up, and then I take the first 4 people and put them in team 1, take the 1 person after that and put that person in team 2, and then the next 3 in team 3, and so on and so forth. So I know how I'm going to break them up. But for every different line ordering, I would again go and chop. The only problem is that some of those will simply give me the same teams, right? If 1 and 2, if person 1 and 2 were swapped, it's actually a different permutation, but they will all go in the same first team. So you're going to count things a little extra. So it turns out that within a team, if you permute all 4 of them, right, you're not going to change the team. It's still going to be the same team. And that's why you divide n factorial by n1 factorial. Then in the second team, you divide by n2 factorial, then n3 factorial, and so on. Did that make sense?
You know, I don't know if I don't know if I like understand the problem conceptually. Like I feel like I don't like like I don't even understand the problem
Okay.
conceptually.
Okay. Ricky, you have a pen?
Would you like a marker?
He usually has
I
one.
guess you have markers. I have markers too.
Oh, thanks. That's good. Thank you, sir. All right. So I've got n people. Okay, I've got n people. I can number them if you want. Right?
Okay. Okay.
And I'd like to break them up into teams. So let's say I tell you I want 4 people in one team, 2 in the other, 1 and 1.
Okay.
So I want to make 4 teams. The first team should have 4, second team should have 2, third team should have 1, and the fourth team should have 1. Fine?
Okay. Yeah, I see. Okay.
So I
okay.
could do it this way. I could chop one that way. I could make these 2 in one team and those 2 in one team.
Okay.
Right? That's
okay.
one way of doing it. I could change things and change the teams. Each one would give me a different way of assigning teams.
Right, like you can assign you can assign the people differently.
Correct.
Right.
Exactly.
Yeah.
So question is, how many different ways are there?
So like with I guess like how many ways are there to do 4, 2, 1, 1? Like
No. This is fixed. This is fixed. This is given to you. This is what I would call as n1, n2, n3, and n4.
So
I'm
out of
telling
8
you,
people-
okay, let me finish. I'm telling you beforehand that there need to be 4 people in the first team, 2 people in the second team, 1 in the third, and 1 in the fourth. This is fixed. This is told to you.
Oh, okay, okay.
And you also know that n is equal to 8, which means there are a total of 8 people. This also is fixed. Now the question is, how many different ways are there to form teams for those with those constraints, right? So I could put 1, 2, 7, 8 in the first team, or I could put 1, 2, 7, 6 in the first team, and so on and so forth. So there are so many ways of doing this. Question is, how many ways are there to assign all the teams?
Oh, okay.
And it turns out that the answer is n factorial divided by n1 factorial, n2 factorial, n3 factorial, and n4 factorial, which in this case is 8 factorial divided by 4 factorial, 2 factorial, 1 factorial, and 1 factorial. Okay?
Okay. Oh, okay. I follow now.
And one way, if you want to think about this in a simpler way, the way I remember this usually is to say, hey, I'm going to take these 8 people and line them up. Now, how many different ways can I line them up? There are 8 factorial ways of lining them up. We know this, right? Once I line them up, I'm going to take the first team, which has 4, the next team that has 2, the third team that has 1, and the fourth team that has 1. I'm just going to follow this rule and always assign the teams in this manner. Now, the only problem is there are many of these permutations where I will essentially get the same team again. Even so, if I permute all these guys here, it's not going to change the team for me, right? So for 4 factorial different orderings, I will have the same team. So therefore, I have to reduce this 8 factorial by that amount. And that's why I get 8 factorial divided by 4 factorial. Got it? So that takes care of the first term. And then same thing over here. I could permute these guys, and it won't make a difference, right? Even if I line them up in a different order within this team, it's not going to change the composition of the teams. So therefore, I get this other 2 factorial and then the others. So it's quite easy to remember this. If you have only one team and they all have to be together, there's only one way to do it, because it's 8 factorial divided by 8 factorial, right? So that's what this partition problem is. And this shows up in in some problems, so you have to kind of watch out. Now, yeah, this is another question where what if they're indistinguishable? Well, it's a minor change. It's still going to be 1 because it doesn't matter which 4 people you put in the first team. It doesn't matter which 2 people you put in the second team. You're just going to get 1, right? Okay. Well, now let's ask a different question. This says you're given n workers. They're all identical. Think of them as fishes or something. Doesn't matter, right? And the question is, how many ways can you partition them into teams? Well, this one's a much harder question. So even if I told you that I want to partition them into 3 teams, then you could have no people in the first 2 teams and everyone could be in the last team. Or I could have all the people in the first team and nobody in the last 2 teams. Or I could have 1/3, 1/3, 1/3 in the 3 teams. There are so many different ways to do this. This is called the partition problem. Essentially, you're asking how many ways can I take number n and break it into smaller numbers. But I haven't even told you how many teams, so the number of teams is also a variable. So this is a slightly harder problem, and it becomes slightly easier if you're told that the largest team is of size k. But this is called the integer partition problem, where you ask, how many ways can I partition the number 8? So 8 can be just 8, or it could be 7 plus 1, or it could be 6 plus 2, or it could be 6 plus 1 plus 1, or it could be 5 plus 3, and the thing goes on. So there are lots of ways of breaking down 8. Each of these gives you a different set of teams. And there are ways to count this. It's a little complicated. You have to write down a recurrence relation. So yeah, and there are variants of these questions. We'll talk about this a little bit later. But it's a partition is a worthwhile problem that also shows up in the competition sometimes. What I'm trying to do, by the way, is for you to familiarize you with all sorts of counting problems, so that if you see them, you know what to expect. Okay. One of these things should work out, and you already know that for the competition you can take cheat sheets, and so you can write down things that you can't keep in your head, and then take them there. Yeah. Here are some variants of the problem. Given n workers standing in a line, how many ways can we form teams for m tasks so that all members of a team are consecutive in the line? What does this mean? Well, it's very similar to what we were doing here. We have a line, in this case with n people. N people. And you need to break this into m tasks or into m groups, and you want people next to each other to be in the same team, right? So if you want to break this into m teams, you could break this up like so, or you could break this up in a different way. Again, this is very similar to the partition problem, except that here you're told that you need exactly m numbers. So if you're told how many different ways 8 can be broken up into 2 numbers, you know the answer is going to be either 7 plus 1, 6 plus 2, 5 plus 3, 4 plus 4. In fact, that's all you have. It depends on whether you want to allow 0 or not. That the problem will typically tell you whether that's allowed or not. Okay. And you'll see that this actually just comes up to, well, if you can identify this as team 1 and this as team 2, then you should also include 3 plus 5, 2 plus 6, and 1 plus 7. And if you do these, then you'll see that you'll get n minus 1 as the possible options, because if you're trying to get 8, this has to be n minus 1, n minus 2, n minus 3, n minus 4, and so on, right? So depending on how you think about it, you should be able to count these things somewhat easily. So some problems turn out to be easy and some are not so easy. Here's another one that's not so easy. So you're in some country, and I think we looked at problems like this last time when we were doing this, this money counting thing. You have a country where you have a $9 bill, a $17 bill, $31 bill, and a $1,000 bill. How many ways are there to change a $1,000 bill? So you're not using the $1,000 bill, obviously. You're only using 9, 17, and 31. You want to know how many different ways those three numbers add up to 1,000. It's a bit of a crazy question, and it's somewhat related to what we were doing the other day with the table, but it's a little harder than that. So again, this is a counting problem. This time you're not seeing whether it's possible to make it to 1,000. You're actually counting the number of ways. And the recurrence relation we wrote down then, we can modify that for counting this. And we can go over this problem a little bit more.
Does the order matter or no?
It shouldn't. No, actually it shouldn't.
Okay.
Yeah. You're asking whether to go from smallest to largest or largest to smallest.
No, I'm saying like, so are you just saying the number of bills? Like the order we pick
Yeah.
the bills matters or no?
Right. So, well, so this is why the bills are identical. Two $31 bills look exactly the same for all practical purposes. So you want to know how many ways to break this up. So this is similar to what we're doing here. We're looking at 1,000, and we want to make either 31, a team of 31, or a team of 17, or a team of 9. And you want to add up to 1,000, right? So you can see that these are all somewhat closely related, but there are subtle differences, and you have to kind of watch out, okay? So this brings us to the integer partition problem, which I talked about, saying how many different ways can you partition a number n into a sum of different integers, positive integers. So because it's positive, you know that 0 is not allowed, right? And your sum can have either one item or more than one item, it doesn't matter. So simply 8 is allowed, 7 plus 1, 6 plus 2, 6 plus 1 plus 1, and so on and so forth. But you can't stick in zeros there, okay? So it turns out that there are ways to answer this question. We can write this as a formula for P of n, where P of n is the number of ways to write down n as a sum of integers. And the way to do this, there are various ways to do this, and if you maybe in your discrete math class you've looked at problems like this, I'm not sure. But one way to do this is as follows, where you can define two of these things called P of nk and P of minus 1n, where P of minus 1n is the number of partitions that don't choose ones, okay? And P of nk is a number of partitions into k numbers. And of course, we'll try different values of k. So it turns out if you can somehow figure those two out, then you can solve this recurrence because P of n is P of minus 1 of n. So remember, you're not allowing ones, right? And plus you want to do p of n minus 1. So there's one way where you have an extra 1 left, and the remainder would have to be partitioned. So let me try and explain this. You've got the number n, right? So either you could do n minus 1 plus 1, or you could do sum of two numbers a plus b, where a plus b adds up to n, and where a and b are bigger than 1. Okay? So if you use this choice, then there's only one way to write down 1, which means all you have to know is how many ways to partition n minus 1. On the other hand, if you're using this, and let's say you're partitioning it into two things, then it's just going to be the different ways to partition A and different ways to partition B, right? So that's what is essentially written down, but so here you're asking how many ways to partition n, but you're not using ones. If you use a 1, the other one's going to be an n minus 1. So here we are assuming that it's only partitioned into two things, but now these could get partitioned more, so essentially you get as many numbers as you want. Now it's also true that this is basically p of n comma k, where you're asking how many ways can I partition it into k numbers. K could be anything from 1 all the way up to n. Okay? And remember, each of those partitions is different. So these are two different ways to do the same addition. As long as you can write down those things, you're in good shape. Okay? Now, here's a way to write down. So you take those two things that you don't know, which is p of minus 1n and the p of n comma k, and you write down further recurrences for them. Then you use those to fill up a table using something called dynamic programming, and you would have the answer that you want. So let's look at this here. P of nk is this plus this. How did that come about? So this says break it into two pieces, n minus k and k, and then go and partition those numbers as much as you want. So the first level partition simply takes n and breaks it into n minus k and k. Fine? Then this guy here, right, so here all you're asking is how many different ways can you partition it into two numbers. And here, wait, no, that doesn't sound right. No, sorry, I take that back. What's going on? Oh, right. Okay. How did that come about? P of nk. Right, so this here, the second term is easy. Let's assume that one of the numbers is 1. If one of the numbers is 1, you're left with k minus 1 other numbers to break it down into, and your total now is only n minus 1. So that part is easy. If it's not a 1, it could be 2 or 3 or 4, whatever. And for each one of those choices, shouldn't this be k minus 1? of partitions into k numbers. Something is not right here. I'd have to go and check this. I don't know if do any of you see what this is? This step looks wrong.
Shouldn't there be two variables? Like you're subtracting, I don't know why subtracting k and minus k.
Right, so here I'm assuming that the last one is a 1. Here I'm assuming that the last one is not a 1.
You're assuming it's k.
So this should be k minus 1, I think. But also there's no reason for this to be n minus k.
But like if you take like you have to make $1,000 bill and you have 9, 13 and 31, then if you take a $31, then you will subtract from 1,000 and then.
Right, but then you lost one number, so this should be k minus 1, right?
Yeah, but do we have unlimited supply of 9, 13 and 31?
Well, this is not exactly solving that problem, is it? Here you're looking at how many ways to partition. Yeah, and here anything can be repeated. All right, let's see if we can understand the second formula. This one does not allow ones. It looks to me like here we are assuming that the first level of partition is n minus k and k, but then let me look into that and fix it and send you something by email. Not sure what I was thinking there. So it turns out that these partitions are best solved using something called generating functions. And these generating functions utilize something else called Pn times x to the power n. I am going to let me postpone this discussion to later so that it goes with the previous stuff. There's no point in me spending a lot of time when we don't quite follow the first step. So we'll come back to this. So these are all various ways of counting different things, and they all use something called generating functions. In generating functions, you write down a polynomial where it's the coefficients that are of interest. I know all that is going to sound really, really weird to you, but just bear with me. We'll come back to it a different day. So it turns out that there are very clean ways of figuring this out, and in fact you can write down a clean little formula like that and compute this. So I'm going to move this forward. Yeah. So for the question of doing the change, there are ways to do this again using these polynomials. All right, so I'm going to talk a little bit about permutation generation. So how am I doing with time? Okay, all right. So here, this actually shows real code for computing computing all the permutations of 1 through n. Okay, so you're given the numbers 1 through n. So let's say we are given 1, 2, 3, 4. You're asked to write down all possible permutations of this. So in this case, it would be 1, 2, 4, 3, 1, 3, 4, 2, 1, 3, 2, 4, 1, 4, 2, 3, and 1, 4, 3, 2. And you can start all over again with the number starting with 2, and so on and so forth. Each of these is a different permutation. And you're going to get 6 times 4. That's about 24 different possible permutations. And 4 factorial is 24. So we want to write a program that generates all these permutations. And it does so in a certain order. So this is a piece of C code from one of the books. And it's worthwhile to try and run this and understand this. You can easily convert it to Python or Java as you wish. It's not that complicated. There are a couple of, this is a recursive program. It's called visit, and visit is called again over here. So it's a recursive program. And there are a few global variables here. So it's worthwhile for you to know that n and level are global variables. Okay? So you're given the number n, and you're asked to write down or write a program that generates all possible permutations of 1 through n. Okay? So the question is, how do we go about doing this? We could, I'm not sure what you would like to do. If you want to go through the code, I'm happy to do that. But we could try and focus on this from a high level and see if we understand it. So it turns out that it uses an array. The array is called value array. And the value array will contain the permutation. To start with, the value array is going to have all zeros. Okay? And then it will slowly, step by step, fill up one item at a time. When it has filled the n items, it knows it has a permutation and it's going to print it. So the print permutation happens whenever the array is filled up. And when it's filled up, it'll backtrack and go and produce the next possible permutation. So in this case, it may start with this permutation, and then it may go and produce you this, and then this, and so on and so forth. All right? So to start with, the array is initialized to all zeros. The level is set to also to 0, so that once it comes in, it becomes 1. And you start filling in items with the value of level. So the first time around, it's going to fill 1 at different places in the array. But it'll fill up the first one, 1, 0, 0, 0, and it will make a recursive call. So after doing that first step, it's going to go off into the recursive call so that it goes deeper into the recursion. When it returns from that, it's going to backtrack and reset the 1 to the second location. Then it'll set it to the third location, and then the fourth location, and so on and so forth. Okay? Each of those is a recursive call, and when it comes back, it resets it to 0, and then goes back and puts it in a different place. Okay? So it starts with that, and when the level is 1, you'll see that one of these things will happen. 1 will get put in one of the locations. And you can see here that there is a for loop which allows it to put first in the first location, then in the second, then in the third, and then in the fourth. But for each one, it'll go and generate all the possible permutations that places 1 in that location. So it's going to generate all the permutations with 1 in the first place first. Then it will generate all the permutations with 1 in the second location, then in the third location, and so on. Okay? Are you with me so far?
I have a question.
Yes, Ian.
How do you get different vowel arrays? Is that just
How do you what?
How do you get different vowel arrays? You just get
So,
multiple arrays, right?
right. So we're assuming that n is given to us. So n is a global variable. So let's assume n is 4. The val array to start with is all zeros. And there's a variable called level, which gets incremented every time you make it go into a recursive call. So the first time it'll be 1. If you make a second call, it'll become 2, then 3, then 4. And if you ever hit level of n, it'll print the permutation, and it'll jump out. But when it jumps out, it reduces the level back. So it goes back to a previous level and figures things out. So that's why it starts from that, from 0, 0, 0, and then it will go here. That would be the first recursive call where level is 1 and the number 1 is put in the first location. By the way, all of these here on this column are level 1 actions. Okay? So for each level 1 action, it's going to do a bunch of different level 2 actions. For each of those, it's going to do a bunch of level 3 actions, and so on. And each one is a recursive call.
Yeah, what I don't understand is like, there's only one array, right?
There's only one array. Yes, but when it backs off, it puts back 0. Whatever it did, it undoes this.
But it only prints when level is n. So
Correct.
isn't it going to erase?
Yeah, so printing is not erasing, of course. So that's why, so let me follow the logic a little bit longer. I start with that. When level is 1, I'm going to start with just the top one here, right? Just this guy here. Let me do some annotations here so that you can see. So I'm done with this. I am here, right? And then I go to 2, and it'll find the first 0 location and put the 2 there. Then it finds the first 0 location and puts the 3, because it's now in level 3. Then it'll go to level 4, where I'm going to get 1, 2, 3, 4. Then it backs up. Okay, and there's nothing more to be done there, so it'll actually go off and make the next recursive call. And there it finds the 0, and it'll put the 4 over there. So the top one doesn't, there are no more options to deal with. And in fact, it's just going to, you'll see that this doesn't do anything more there. Okay, and when it backs up, it will go to this option and put the 4 over here, and it'll generate 1, 2, 4, 3. So the second thing that it'll generate would be 1, 2, 4, 3. And then it will back up here, because now it's done with all the options on this end, right? And then you'll see that it will go off over here. And when it's going off over here, all the things that it had put, where it had put 3 and 4, have now become zeros, because when it finished the iteration, it sets back to 0. All right?
Yeah.
Roughly.
That's a little bit different.
So
Okay.
so you have to actually run this through to convince yourself. This is why I wanted to spend some time with it. I would really love for you to play with it. It's not complicated code, or at least it's not long code, and you can play with it,
No,
right?
it's not complicated.
Yeah. And then, so the next thing it should print for you should be whatever options you get over here. And this time you're going to get 1, 3, 2, 0, right? Because if you follow the options for here, you're going to get 1, 3, 2, 0 and 1, 0, 2, 3. Because it's going to find the first 0 and put the 3 there, 1, 3, 2, 0, right? And then it'll take the second 0 and put the 3 there, and that'll give you a 1, 0, 2, 3. Did that make sense?
Yeah, this is a lot more complicated than I thought it was.
Yeah, yeah. Well, there are many versions. I don't know. There may be more intuitive, more simpler versions, but I like this version, so I'm going to just stick to it. So the first one, when it goes to level 4, will give you 1, 3, 2, 4. That's actually, this should have been before. And then it'll give you 1, 3, 4, 2. All right? So these two options here, the 0 will get a 4 and it'll become 1, 3, 2, 4. This 4 will and it'll become 1, 4, 2, 3. So I got that wrong. Is it? Yeah. Okay. And then it will go over to the 1, 0, 0, 2 option, and it'll give you 2 more. So here, 2 will be over in this end. Oh, I erased something here. 1, 4, 2, 3. Then the 2 will come over here. You'll get 3, 4, and you'll get 4, 3. So this is the order that it should print, and you're welcome to go and check and okay. And then after this, it's going to start all over again, but with 1 in the second location. Does that make sense?
Not really.
Not really? So you're over here. You just finished. You went through this branch. You finished all of these options. So now it's going to go to this option where 1 is in the second place. Did that make sense? It's back to level 1. And you can see here that it tries different places to put this value.
So that'll be visit 1.
It'll still be visit 1, except that it'll find a different 0 location to put the 1.
Visit 1.
Sorry?
No, I'm just trying to think.
Yeah, yeah. So when you had 0, 0, 0, 0, you started with this. The first time, it found the first 0 and put the 1 there. And then went and did further work. Then this says, well, also try the next possible location of a 0, and that would be this location. And so it's going to go back, put 0 over here, and put 1 over here.
So the first time visit runs, it also calls visit I through n, right?
Correct. But remember, in between those, so the nasty thing is that in between these for loop iterations, there is a visit. So visit means it's going to go down that recursion tree.
Right. So then you do like visit 0.
Yeah.
And then visit 0 is gonna
Right, so
Oh, visit 0.
I didn't have place to fully draw that thing. I can draw it here and show you.
So it like branches off.
Sorry?
So basically, is this function just find the factorial of k?
It's not computing the factorial of k, but it'll print out k n. Actually, it's n factorial different permutations. Yeah. Yeah, its time complexity is n factorial, but it's a systematic way of just printing all the permutations.
I guess the part that's confusing me is this array is going to be local to each call of visit, right?
No, no, no. The array, almost all the variables are global variables here. That's the only thing, except for k.
I guess
Except for k, everything is global.
becomes
Yeah.
you're doing this very like crazy dance.
Yeah.
Printing the array and modifying it at the same
Yeah.
time.
So,
Like,
yeah.
you know,
So let me try and show you. So you have 0, 0, 0, 0. That's the status of the array when you start. Then it puts value k equals level. So when level is 1 and k is 1, it's going to put a 1 over here. Okay. Hold on. Yeah. And then it's going to if level is not n, then if you have a 0 somewhere, it's going to call visit and go into the next level. Okay? So from here, it'll go to the next level, and it will find the first 0 location. Because it's in level 2, you're going to end up with 1, 2, 0, 0. Okay? Then it'll make another call from there, go through this. It'll find it still finds a 0 in the list. There is a 0 here. So it'll go and make a recursive call, and you'll get that. And then, of course, you're going to get 1, 2, 3, 4. And at that point, it'll see that you've reached level n, and it'll print out this permutation. Okay? Now what happens? If it sees level n, it falls down here, reduces the level to 3, and sets the last thing back to 0. So this guy here becomes 0. So it comes back to this.
yeah.
So you're here at this state. Now what
You already
happens?
printed.
Sorry?
At that point, you already printed your.
You've already printed 1, 2, 3, 4. Okay? Now the question is there anything more to print? You'll see that it cannot find a 0 anymore, and so it's going to go back to this point. Okay? And now what happens? It's halfway through the for loop where it put the 3 in the third location. So it's going to go see if there is one more 0, and it will find that, and that's where it'll put the 3. Is that clear?
Right.
So
What
this is
did
the
it-
part that's tricky.
Yeah, why did it reset 0? What was
It didn't reset 0. So remember, when it comes back down here at the end of the recursive call, it resets whatever it did, it will undo it. And it only undoes the last step. So that became a 0. Now at this point, for 4, I have checked the only 0 that's there. There is nothing more to do, so there's no more recursive calls. Okay? So this here was the recursive call from here. This was the recursive call from here. Now, this one has a second recursive call because there are 2 zeros. So it's already finished placing the 3 in the first 0. Now it's going to go back and do it in the second 0.
Right. This is a really efficient algorithm.
It is. It's very efficient. Yeah. Oh, yeah. So now it'll go through this step, and it'll get you 1, 1, 2, 4, 3. And it'll print that out.
Yeah,
Okay?
I got it.
And then you'll go back, and what happens now? Yeah, you're going to try 1, 0, 2, 0. Is it? Yeah. Yeah, I believe so. And you're going to get the possibilities for this, right?
Yeah.
Then you're going to get one more, and that's 1, 0, 0, 2, and the possibilities for that. And then it'll back up all the way here and put the 1 in the second location. And then it'll restart that process. Sorry. Thank you. Does that make sense?
Yeah, I get it.
Yeah. Try it. I think it's really worth your time. It'll also give you a really good understanding of recursion.
For sure.
Yeah. And yeah, make sure you understand that only k is a local variable. Everything else is global. Okay. So this helps you to write down to generate all possible permutations. How am I doing with time?
It's 40.
40? Okay. So this helps you to generate all possible permutations, which means how do you make n people stand in a line? How many different ways can you have n people stand on a line? And there are lots of related questions, and you have to kind of know this. You can also modify this for circular permutations. Remember we asked how many different ways can n people sit around a table? Well, it's very easy here because you fix one person and then you permute the rest. Okay? So you can go back and look at some of those problems and see which ones can be a simple modification of this. All right, here's a well-known problem that you can solve with the permutation problem. It's called the traveling salesperson tour. In the traveling salesperson tour, you're given a graph, and you're asked to, well, there are various versions of the problem. Let me tell you the popular version. The popular version is to find the tour that's cheapest, where the traveling salesperson has to visit every city and then come back to the start point, except that you want this to be done with the smallest possible total tour length. And then the question is, how do you find, well, a variant of this could be have it list all possible tours, and then you can, obviously if you list all possible tours, you can find the one that's the best. So just a simple modification of the previous algorithm. Everything, in fact, should look the same. There's one minor change here. You only put something in the next step if it's adjacent to the previous one. Remember, it's a graph. So if you're going from here, from Miami to Tampa, well, there better be a road or a flight to take it. Otherwise, you cannot, right? So it checks whether the next step is adjacent. And if it is adjacent, and if it is a 0, it places it there. OK? Otherwise, there's no difference. It's just a minor variation of the previous one. Yes, Dimba?
I think in that if statement, the adjacency list, maybe instead of k, it should be a value of k, because it depends on what value you picked previously. Right?
Is it?
I think so. Because k is the index, right? And then the actual value is.
Yeah, you are not going from value of k. Wow, that's, I don't know. Should that be k or value of k?
Because the way I'm thinking about it,
Mm-hmm.
If you have, for instance, the permutation 1, 2, 3, 4, you
Right.
have edge from 1 to 2, and edge from 2 to 3, and edge from 3 to 4.
Right, correct.
And then if you're filling out the values, in order to know what the previous one was, it's the value, the val of k that gives you.
Well, in that case, you need I minus 1, not I, no?
Well, yeah, it's a val of I minus 1. No, it's k, val of k minus 1.
Look, this suggests that you're now messing with I. Now, what is K? K is the current level. Isn't K the current level?
No, levels.
Level is the current level.
Yeah. That's my level.
K is just a temporary variable, local, means nothing. Yeah, okay. So what are we doing here?
No, k means something. K
K is
is
a number.
what you previously visited, right? Because when you visit,
No, K is what you're visiting. So I is what you're visiting next,
yeah, so
right?
I becomes
So I becomes K.
recursive form.
Correct, right, right.
So which means you care about the value of I, right? Because that's
It's,
what you just
and it's only there in that recursive call you're actually going to put that, you're going to put that value, you're going to put something in this location I over there. So I see. So K is the previous one, I is the next one. So I don't see anything wrong with it. But you're saying it's not next to each other in the permutation. That's what you're saying?
The thing is, k seems like it's just an index, right? It's not the actual level. And what you want is the level, is the level of the previous one. And k in this case is just the index, I think, right?
Yeah, it is the index.
Because when you visit, I becomes k. And
Okay,
I is the thing.
let's try something over here. So let's say we are somewhere here.
Okay.
Right? So we make this the so K is this guy here, okay, because that's where we just put the value of 2.
No,
K is this guy here.
That guy is not 2. In that case, k will be 1.
Well, here the index and the value are the same. Okay, for now, let's just go with that.
Let's assume
Yeah,
the index and the
let's just go with that. Okay, or if you prefer, let's go here. K is over here. Okay. And level is 2.
Yes.
So this is level. And then it's going to make this as the I. Is it? Yeah.
It's going to make any zero.
Sorry?
It's going to make any zero be that.
It's going to make any 0 be the I. Correct. Well, it's going to make the first one and then the next one and then the next one.
So whichever first zero is going to be
Right.
first.
So the first time around, it's going to make that one the I, then it's going to make this one the I. But that doesn't help me. So I think you shouldn't think in terms of arrays. Instead, think in terms of what is the order of vertices you're going to visit. So K is the vertex you're visiting,
Oh, makes sense. It should
right?
be k, yeah.
It should be
That's-
K
that's
because
the
you're
one.
just, it's the order of vertices you're visiting. And it's just checking whether K is the previous one, I is the next one. And it's checking whether they're adjacent.
Okay, but then you're not assuming the path comes from one to the next one to the next one, right? Because you might have a path from 2 to 3, but you don't necessarily have a path from 1 to 2, 1 to 3, right? Like in the sample case you just talked about.
True, true.
Maybe it should be I minus 1 instead of a, like a value of I minus 1, because that will definitely tell us what the previous person is.
Okay, so your question is, how is it ever going to generate this path 1, 3, 2, 4? Let's say these edges exist, right? So in level 1, it puts the 1. Then it goes to level 2 and then checks which ones are adjacent to 1. Which makes no sense. That's a good question. I don't know. I think you just have to go and try this. Not sure.
I think it might even have to check both what's next and what's after, because you need a path from 1 to 2 and then 1 to the next one, from that one to the other one as well.
Yeah, I can send you a link to the text that has this code. It's not mine. So I doubt if there's a mistake, because this guy is very, very good.
Yeah, then I'll probably just go
But
over it and
yeah, please do go over it. I'm pretty sure it's right. It's just that I'm not seeing it right now.
So Professor, you think that adjacent of ki, like that, what do you call it? Like that if statement is checking if you have a path between the two nodes.
If there's an edge between
So
K,
like let's say
K and
you're
I.
trying to go from here to here, so just to see if there's a path like
Not
that
path,
goes
an
from here to
edge,
here,
yeah.
or like an edge that goes from here to here.
Right, correct.
Oh, yeah, because you're
Remember,
comparing it, like,
traveling
going
salesperson
from
tour
A, yeah.
will only follow edges.
Right.
So this checks, this is just an additional test besides the permutations. In permutations, you don't have to care. You just put down the different orders. Here, you can only go in that order if each of those has an edge. Yeah. So why are they checking an edge from K to I? And I don't have an answer. Sorry.
I mean, I think it's correct. The only thing is, when you print it out, maybe the path itself is not from 1 to 2 to 3. It's just telling you that this permutation has a valid path that starts from one of these guys and ends with one of these guys.
It can't be. It has to be very precise there.
It has to be one position.
Mm-hmm. Although permutations can be thought of in 2 different ways, so maybe that's where the problem is. And this is a problem I've seen before. Let me just show you. If my permutation, let's say, is 1, 4, 2, 3, right? So this says that I go from 1 to 4 to 2 to 3. That's one way of looking at it. Another way to look at it is that it goes from so another way to look at it is it goes from 1 to 4, then no. So this is the standard way of looking at it, 1 to 2 to 3. Okay. The other way to look at it is whatever is in 2 is now sitting in location 4. Okay, so it's actually 1, 2, and then this is whatever is in location 3, and then this is something is not right. What's not right? What?
1, 3, 4, 2.
So 4. So 2 is in this location. 3 is in this location. Yeah. 4 is in this location. So this is another way to think of the path. If this is what he or he meant, then would this now work out for you?
Think about it more, but maybe it's a possibility.
So you can see that this is a different permutation, right? Here the path is different. You're always going from wherever 1 is to wherever 2 is to wherever 3 is to wherever 4 is, but then its index is what decides the order. It may be. This is the only way I can think of that suggests that there may be something different.
Well, Professor, like in the let's say in the bottom one, like in the
Yeah.
like right in the bottom permutation that you wrote, as opposed to the top
Yeah.
permutation. So in the bottom you go from 1, like basically you go from
1 to 3 to 4 to 2. Yeah.
So basically you visit them.
So even though I've written down 1, 4, 2, 3, I really meant this path. So the permutation is this and the path is this. Right. So people write permutations in 2 different ways. Okay. One is to simply write down what is where. Okay. So 1, 4, 2, 3 is a permutation. All right.
Okay.
Another way to specify permutations is to say where you can find a certain item. Okay. So if I gave you this as an array 1, 4, 2, 3, I am going to interpret this as follows. I'm going to say that 1 is found here because it says 1. 2 is in location 4.
Okay.
So that's 2. 3 is in location 2. And 4 is in location 3.
Oh, so those are locations.
So think of those as locations, not as the actual permutation values. So now your permutation looks like this. So I know that some books write permutations like this. It's possible that that's what this guy meant. And I think maybe this adjacency will work out right if you do it this way. Because now you're first putting where 1 is. Next you're going to put where 2 is. Right? So let's say you put 2 over here. How does that help you?
Well, Professor, does it have anything to do with the order in which you visit the nodes?
Yeah, that's what we're trying to nail down. So these are 2 different ways of expressing the same permutation. We want to know which one is the real ordering of the vertices to be visited. So permutation is different from the order in which you visit the vertices. If it were this, right, then this would be k and this would be I, and it makes sense to say these 2 are check whether they are connected. I think. So if this is connected to this, then 1 to 4 is possible. If this is connected to this, then this is possible, and so on and so forth. So I think it may be a problem in interpreting the permutation.
Yeah, that's what I think. I think what you said.
Yeah.
makes sense.
So please take a look at this and make sure you understand it more and tell me more next time. Yeah. But I think we're pretty close. So I have 2 more problems left. One is the generating a power set. Anyone know what a power set is? You've heard this before? It's the, sorry?
I haven't.
You haven't. Anyone?
It's the set of all possible sets.
Set of all subsets. Okay. So if your set has 1, 2, 3, 4, Your subsets could be the empty set. It could be the singleton sets, 1, 2, 3, and 4, or it could be pairs, or it could be triples, or it could be all of them. So the question is, how many different subsets are there in the power set? That's the first question. And then the second question is, can you write down all the subsets?
Well, that's 2 to the power of n.
So it's 2 to the power of n because in each subset, each item is either present or not. So it's either a 0 or a 1. And so now you have n items. So that almost looks like an n-bit array. And each item can be a 0 or a 1. And how many different binary numbers do you have? Each of those corresponds to a subset. Right? So therefore, there are 2 to the n subsets in the power set. Clear? Okay, so next question is, how do we generate all the items in the power set? For that, we just have to know how to write down all possible binary numbers of length n. If we did that, we would know how to write all the subsets. For writing binary numbers, there's actually a simple algorithm for it. And I'm just going to show you. I still have a few minutes.
I thought you wanted the markers.
No, I have a marker. Do I still have a few minutes, or am I out of time?
Well, technically no, but.
Technically no? All right. So let me just say that you can start with 0, 0, 0, then take the last 0 and turn it into a 1. And if the last bit is a 1, then you change the 1 to a 0 and change the first 0 to a 1 and stop there. Then the next one, again, this is a 0, so you change that to a 1. Now you go from here, change all those 1s to 0s and change the first 0 to a 1, and that'll give you the next binary number. So there is a very simple algorithm for generating all the binary numbers of length n. You can easily write code for this, I'm sure. And once you do this, you can turn this into subsets, because every 1 corresponds to a subset. Think of this as item 1, 2, 3, and 4. So this here says I have item 3 and 4. This here says I have item 2 and nothing else, and so on. So there's a strict correspondence between subsets and binary numbers. So it doesn't matter which one you write code for, you can easily convert one to the other. And finally, you have this problem of generating all possible combinations. So if I have n items, how do you choose k items from there? Write down all possible such combinations. We'll do this next time. It's actually quite nice, and there's a short algorithm